Today we are going to discuss about the factors affecting the test results. In the last lecture we discussed about how the strength is being affected by the specimen type and how the fracture plane is being formed in a concrete, and how the cube strength and the strength in the structures are being related. And in this lecture we will be discussing about the factors affecting the strength based on the test conditions. Factors affecting test results. How the test results will vary based on the n conditions which we are giving during the testing. First, n conditions and capping. Second is based on size, shape and aspect ratio. Third, based on rate of loading. Again, when we talk about strength, it obviously refers the compressive strength of the cube. So strength refers to the cube compressive strength. Assume this to be the cube and we are applying load in this manner, and we are obtaining the results based on F equal to P max, that is a maximum load divided by the cross sectional area. Through this we will be determining the compressive strength of the cube. Being so, how the test results are being influenced by the n conditions, that is the thing we are going to discuss now. The test conditions induces variations in results. In the last lecture we discussed about cube strength, and this cube strength and the strength in the structure will be different, since the strength in the structure is being influenced by many properties. The both will not be the same, but we can just relate the strength based on the materials that have gone inside during the concrete making. Based on the relative measure of the materials, we will be able to calculate the cube strength. But the same when it is being used in a structure and it is being influenced by many other properties, the both will not be the same. This is what we discussed in the last lecture. So this cube strength is nothing but it is just the relative measure of the mix that is going for the concrete making. Likewise, here how this n condition will influence the test result, we'll have a look at it. Since the n conditions, I am telling that n condition will have an impact on the test results, then I must standardize the n conditions. Since I am telling that n conditions and test conditions will have an influence on the strength of the concrete, test results of the concrete, then I must have a standardized procedure mechanism for determining the strength, so that I must have a standardized test practice so that I can compare all the tested materials, and based on that I will be able to tell how the strength is being varied based on the test. So, standardized test conditions should be there to compare the cubes. Mainly we use only cubes, so I must have a standard test condition to determine the various cubes, so that I can find out how the strength is being influenced by the test conditions. So by doing so, I will able to compare the materials which is being gone into the concrete making. So I will be comparing how much of materials that is being gone into this concrete for this cube making, and another set of sample. Likewise, I will be able to compare the materials which is being gone into the concrete for cube making. The standardized test condition enables to compare the materials that is being used for making cube samples. So if I have a n number of cube samples, I will be, because of the standard test conditions, I will be able to compare the relative measure of the materials that is has been gone into the n number of cube samples, and based on that I will be able to tell how the strength factor is being influenced by this standardized test conditions. Likewise, not only we can test a cube, we can also test a portion of a beam. Assume this as a beam. This is a portion that is being left over after doing a flexural test. Again here I am applying load, and I am applying load, and based on this I will be getting the strength. So this test portion of a beam result and the test result of this cube will not be the same, will be influenced by many other factors. So this is how, for this reason only we should have a standardized test condition, and also the strength in the cube will not be same as that of the strength in a that comes in a beam. Next, how this end condition and capping. This end condition, the cube which I am testing should have a plane surface at both top and bottom, that is, there should not be any undulations. If it is so, then then while testing it results in stress concentration, and because of that I will be getting a different results and I will not be able to get accurate results. So this N condition is nothing but the Q portion which I am testing, this is the place where the plates will come into contact. So that surface should be plain. There should not be any undulations. So that is the N conditions. If suppose we are going to test a core from the structure, that is from a structure we are cutting one part of that is from a structure we are cutting a part of a element and we are testing it. While doing so, then we cannot tell that we will be able to get a standard shape from the core element. There while doing the cutting and drilling operation we might get some undulations in the surfaces. So while doing so, to prevent the undulations, that is to keep the surface truly plain, we will be doing this capping. That is, sometimes if we do not get the desired length or the depth of the specimen from the structure where we have drilled it, that times we can do this capping. That is, we are filling that portion to get the required length or depth of the specimen. So that is known as capping. We will be putting some materials so that we will be able to get a standard size of the material before testing it. That is called capping. Then if this capping is done, then it influences the strength results. Why this capping influences the strength result and how it does, we will see in detail. So this capping is again nothing but it is done to bring the specimen to the required length and the depth before testing. So that capping also influences the strength results. How that strength difference comes is, the strength difference is because of the lateral expansion of the capping material and concrete. Supposing this is the specimen which I obtained from the core and it is not in a standard dimension, so I am doing some sort of capping to get it into the required shape, and this is like this, the capping will be there. So after doing this capping, again I will be placing it in the compressive strength machine and I will be applying load, and based on that I will be getting the strength result. The different capping materials which are available are alumina, cement, gypsum, plaster, sulfur, plaster of Paris. These are the different capping materials which are used to make the specimen to get into the required shape and size. So by applying this capping materials, the specimen is ready for testing. How this mechanism, how the test results is being influenced is discussed in this mechanism. Assuming this to be my cube, I am applying load. Here let us assume that we are not done any capping for this specimen. It is the cube specimen and I am placing it in a compressive strength testing machine, and I am applying load through the loading plates or platens. Both are same loading plates or platens, and I am applying load through that. When I am applying load, what happens to the specimen? It tries to, here when I am applying load, this surface and this steel platens will be in contact with each other, so there arises a frictional force. Likewise, at the bottommost surface and the platen will be in contact with each other, and there arises another frictional force. Likewise, here and here. So there arises a frictional force where the steel platens and the concrete both comes in contact with each other. So this force will be, this frictional force will be much stronger at the ends, and it gradually reduces from the top. Likewise, from the bottom also it starts gradually reducing towards the middle. Likewise, the same happens here. So the frictional force, which was more at the top and the bottom, is being gradually reduced towards the center, and this mechanism is called as Platen effect. This is called as Platen effect. That is, however we are trying to apply a uniaxial compressive force, the material will try to, we are applying uniaxial compressive force, the material will try to compress, but this frictional force will act in this manner, and this is the reason why we got the shape failure of the uniaxial specimen in this shape. Here an opposing force is acting to the horizontal or transverse movement on load application. That is, we are applying load, but there is a frictional force acting in this direction, that is the opposing force to the horizontal movement, and that is the reason why we get the failure pattern of a cube in this manner, and this effect is called as Platen effect. Being so, the Platen effect, that is, the frictional force is acting and it is being reduced when it is come to the mid of the specimen, and that's the reason how we get the shape of the failure specimen, and in that manner which we discussed in the last lecture, that was the failure pattern of the cube when the cube is being subjected to uniaxial compression. Now, if suppose I have some sort of capping to my material, which is to be tested. Because of that Platen effect, how it will behave. So based on that Platen effect, we will be getting the strength. So suppose if I have some sort of capping using the capping materials which we discussed now, like alumina cement, plaster of Paris or sulfur, if any material is being filled here, then at that time how the strength will be influenced because of this capping. So based on the capping material, the strength influence will vary. If suppose Poisson's ratio of capping material is more, and modulus of elasticity of concrete is less, then what happens? It actually will tend to nullify the Platen effect. Since the Poisson's ratio of the capping material is more, the frictional force acting here will not allow this material to expand more, and if so the modulus of elasticity of concrete is less, then actually that kind of Platen effect which we see in a cube without any capping material will actually tend to nullify here. That is, we will not observe any true Platen effect in the material, in the capped material. If suppose if we have higher mu by E, then it results in higher lateral movement. That is, the soft materials will tend to move. The soft capping material will have, soft and weaker materials have higher expansion when compared to strong capping materials, and that will influence the strength results. If it is lower, less lateral movement, when we are using this soft material which has a high expansion, then compared to concrete, that material will start moving in the lateral direction and the concrete will move somewhat relatively in a lesser manner. So based on the type of capping material which we are using, that also will influence the test results. If suppose we use a capping of low restraint, then how my failure pattern will be? My failure pattern will be in this manner. That is, the cracks will grow parallel and it starts to fail. If suppose I will use a strong capping material, then that time I will be having a failure mechanism of this manner. That is, the concrete alone will be subjected to the loads and this capping material will be strong enough to resist the lateral movement. So I will be getting failure pattern in this mechanism. If the capping material is not that much enough to withstand the frictional forces, then it starts moving and the failure will be developed. Failure planes will be developed parallel to each other, leading to the failure of the material. And this is all about end condition and capping. The same Platen effect, if we observe it for cylinders, here my h by d is 2. This is for a cylinder, how this Platen effect will be. Here some portion will be left over and the failure pattern will be in this manner. This portion will remain unaffected by the loading condition when we use a cylinder of h by d ratio equal to 2. In case of cubes, the Platen effect will be like this. Here we'll be having some sort of overlapping, whereas for cylinders that overlapping will not be there and some portion will be left out, and that's the reason why we get a failure pattern in this manner. Yes, why we are getting this overlap is since this is, assuming it to be D, this is 0.5 and this is 0.5 D. So some sort of overlapping will be there and the Platen effect will be at a distance of 0.6 D. So some sort of overlapping will be observed in cubes, whereas for cylinders, since we are having the h by d ratio as 2, this overlapping is not observed here, and that's a reason how the cube failure and the cylinder failure are occurring, and this is the reason why we are getting the shapes of the cube failure and the cylinder failure in this manner. Next we will discuss about the loading rate. Higher loading rate yields higher strength, whereas lower loading rate will lead to creep developing in the material. So we should have some sort of constant loading rate, and as per the codes prescribed, as per the prescriptions given in the, as the code prescribes, the loading rate is 14 MPa per minute for cube and 12 MPa per minute for cylinder. So this is how the loading rate has an influence in the strength of concrete. If a material is loaded quickly, then obviously it will give higher strength results, whereas when it is being loaded in a slower manner, then it leads to creeping of the material. So the loading rate is being standardized, and that's being given here. 14 MPa per minute for cube and 12 MPa per minute for cylinder. Next we discuss about the tensile strength. Tensile strength. Compressive strength, we are applying compression load on either side of the cube and we are obtaining the strength results. How to compute this tensile strength of the cylinder or cube? How to determine the tensile strength? It is difficult to measure the tensile strength directly, since the specimen has to be gripped on both sides firmly. So it is somewhat a tedious job to obtain the direct tensile strength. So we go in for a indirect measurement of tensile strength. What are those indirect measure? One is modulus of rupture and another one is split tensile strength. This modulus of rupture we are determining the tensile strength in flexure. When it is in a flexural member, we are determining the strength of, in a flexure member, we are determining the tensile strength of the specimen, and that is called as modulus of rupture. And another indirect measure is this split tensile strength. In modulus of rupture, we will be having this flexural member and we will be applying 2-point loading. This is the point where the beam rests, and this is the point through which the load will be applied. Load will be applied in this manner. If we observe the bending moment diagram, load P by 2, P by 2. L third, if we observe this bending moment diagram, we can see that this portion is being subjected to pure bending and no shear is being influenced in this zone. This portion is subjected to pure bending and no shear is influenced in this zone. So based on this, we will be getting the tensile strength of the concrete. So this 2-point loading is a standardized test to determine the tensile strength of the concrete. That is nothing but modulus of rupture. Likewise, we have 1-point loading, but under that 1-point loading, we will not get this much area subjected to pure bending alone. There will be some shear influence also. So we have standardized this 2-point loading to determine the tensile strength of concrete rather than 1-point loading. Next, in this split tensile strength, we will be subjecting the cylinder to compression load. That is, we will take the cylinder and load it in a compressive strength machine by keeping the cylinder in this manner. The platens will act here. This portion will be subjected to compression. How come to determine a tensile strength? Again, I am using a specimen in a compression machine is a question. Here, what we are doing is, even though the member is subjected to compression, most of the area will be under tension. Likewise, what we discussed in the last lecture, even though a material is subjected to compression load, the material fails because of tension. The same applies here. Only a small portion, that is at the top and the bottom, it's being subjected to compression force, whereas the remaining portion is being subjected to tension. So based on this, I can calculate the tensile strength of concrete. This modulus of rupture and split tensile strength is both indirect measurement of tensile strength of concrete, since this direct testing mechanism where gripping of material is a problem, I am going for indirect measurement of tensile strength of concrete. While doing so, this modulus of rupture will give higher tensile strength value in compared to split tension, and this split tension also will be somewhat higher when compared to direct tensile strength. But somehow I will be getting the tensile strength of concrete. Here the maximum bending, because of this maximum bending in the member, the tensile force at the bottommost fiber I will be able to calculate in this modulus of rupture, and here leaving the top and the bottom portion, other portion is being subjected to tension part, and based on that I will be able to get the tensile strength of concrete.